Okay, thank you for having me, and also to Daniela and Siva for inviting me virtually. So this is a talk about 2Qs with non-stochastic arrivals, and I'm Neil Walton and I work at the University of Manchester. So the first thing to say is this talk is actually about quite an old paper. It's a paper that appeared in sort of early 2014. I wrote it in about 2012 and only presented it once in 2012. So it's called 2Qs with non-stochastic arrivals, and it was in operations research letters. And the paper is about sort of modelling non-stochastic aspects in queuing systems. And one of the models we considered in the paper was about regret and the notion of regret in queuing. And about the same time, or a little bit sort of, whilst I was writing the paper, Deverrat Shaha gave a talk in Eindhoven when I was in the Netherlands, and gave essentially kind of a CMU rule kind of version of this kind of online learning and regret in queuing systems. I don't think Deverrat actually published a paper on that, but certainly he had thoughts along those lines. So why talk about this now, when you're supposed to be talking about your kind of latest research? Well, the reason I decided to talk about it is because there have been quite a few papers appearing recently considering kind of similar models, and so I thought I'd kind of talk about it and talk about why the paper I wrote was written the way it was, and contrasted a little bit against this kind of recent sort of line of work sort of going on, kind of happening on the other side of the Atlantic. And I don't think any of these works are particularly aware of the paper from 2014. So the earliest paper I could find is this paper of regret in queuing bandits, 2016 Eurips, and then I think the kind of journal version of that is just about to appear at Operations Research. There's also a paper covering that kind of same sort of CMU rule as Deverrat was thinking about in the stochastic setting now. I guess that's a preprint at the moment. There's also a preprint by Modiano, and a paper that's appeared also considering this kind of adversarial regret kind of framework that's contained in the paper. So there's quite a few papers with quite similar models there, which made me think that, well, seeing as this is kind of a US conference and I haven't ever presented the work in the US or really outside of the Netherlands, I thought maybe I should talk a little bit about what I was thinking there when writing the paper, what the model entails, and why I sort of have a different view maybe compared to these more recent works, which are really looking to kind of how do we tailor new algorithms for the queuing setting based on kind of results about regret minimization online learning. Okay. Right. So here was kind of the starting point. So one of the great things about kind of these kind of no regret learning strategies, particularly in an adversarial setting, is you don't need to make stochastic assumptions about how your system is evolving. So if we kind of think of it like a classical queuing theory, we can think of results like Linley's recursion. Okay, and here you can start with maybe the queue sizes being equal to 0, and then you can say, you can kind of update the amount of queue size or the kind of workload in the system according to this recursion. So basically, you take the queue size from the previous time step, minus off the amount of service that's happened in the inter-arrival time, and then add on the new amount of service that's just arrived. And unless the queue goes 0, then you get the new queue length vector. Okay, and then if we can iterate on this, and it gives essentially this nice maximization, which says that we can express the sum of the queue sizes as a kind of maximization over the sums of these kind of service times minus inter-arrival times. Okay, and that's a fantastic result because it essentially reduces the single server queuing problem into IID, into a sum of essentially independent, identically distributed random variables, assuming that these ANs and tau n's are IID. So that means that we can start applying sort of central limit theorem results, fluid limits, large deviations, and all the things that we like. Okay, and apply probability. However, what I was interested in was, well, what if this IID assumption doesn't hold in the queuing system? What does that mean, and do we still have essentially a reasonable notion of stability for that system? Okay. Right, so that's kind of the initial kind of high-level question. What does stability mean when you don't have any stochastic assumptions on what's happening in terms of these arrivals and maybe these inter-arrival times? Okay, and so what I considered, at least in the paper, was two different types of models, both where you don't make stochastic assumptions on the arrival processes and inter-arrival times, and then come up with some notion of stability in those cases. Okay, so here's the basic model that that we considered, or the paper considered, and I called it a simple regret queue. And the idea is fairly simple. You have some fairly arbitrary arrival process with associated arrival times, so something that increments by 1 every time an arrival happens. We let Q of t be the kind of queue size process. And then associated with the server over here, there are different service modes belong to some sort of scheduling set S. So what we do is when the sort of kth job arrives to be served at the front of the queue, the server chooses some service mode, pi of k. And then based on that, the amount of time that it takes to serve the job is going to be pi of k, tau of k. Okay, so some function of the service mode decides how long it's going to take to process the job. All right. And so what we're going to consider associated with some policy pi, which chooses the service mode for each job. We're interested in the queue size, which is just the sum of the arrivals since the last time the queue was empty, minus the sum of the departures which have happened since the queue was last empty. All right. And then essentially the metric we're going to be interested in for this system is looking at how the policy behaves in terms of its queue length compared to the policy that did the best amongst the set of schedules. Okay, so sigma belonging to the set of schedules here. All right. And the thing I was interested in is essentially the notion of regret and how that plays a role in the queuing system. So the regret is defined as sort of the sum of how your policy did compared to some fixed policy. Okay, and here I've written it down in terms of the choices of the service times tau of k, pi of k, minus the sum of the tau of k sigmas. Okay, so this is sometimes called the regret over n time steps is this guy. Okay, and now a policy is said to be Hanan consistent if we can bound the regret and show it goes to 0 on average. So we can bound it above by some function f of n, and when I divide by n, it goes to 0 as n goes to infinity. Okay, so sort of this means that the regret is asymptotically equal to 0. Okay, and one thing I can say is that Hanan consistency is also equivalent to another result which is called Blackwell's approachability theorem. Okay, Blackwell's approachability theorem says, can I get some vector on average to converge towards some convex set? Okay, and Hanan consistency is this notion of if I sum up rewards, do I do well compared to the best fixed policy? Okay, and the two notions are equivalent to each other. Blackwell's approachability theorem is also can be thought of as a kind of vector version of the minimax theorem. So the idea you can kind of swap minimizers and maximizers in an optimization. Okay, so we'll come back to that comment a little bit later, but it's just something to have in mind. Okay, so the theorem that the paper proved is that if you've got a policy that's Hanan consistent, okay, and you've got some bound on the service rate, okay, so nothing's going to take forever to get served, you're never going to get completely jammed, then you can prove that the policy that you get is always within a little o of the best of the fixed services. Okay, so if there's one server that is the best in your system, then your policy will behave comparably to that. Okay, so in other words, this can be interpreted as saying as if there exists a rate stable fixed policy, then the Hannan consistent policy cannot be unstable. Here, by unstable, I mean that the Q length drifts off linearly to infinity. Okay, so always going to be sort of essentially rate stable. Okay, the proof is not too hard. You have to remember that we're kind of essentially swapping in the regret bound, which is to do with sums, into that linearly recursion that we mentioned earlier. So essentially, the proof, which is not too long, it's a page or so long, involves plugging in regret bounds into kind of renewal theory type bounds associated with the linearly recursion. Okay, so it's not too difficult to prove, and like I say, there are similar results coming out now, considering the stochastic and adversarial setting as well. So in contrast to those kind of more recent papers, the more recent papers seem to be focusing on, can I come up with a new policy based on the kind of rationale that you use for kind of regret minimization? Whereas this result was more saying that, well, it doesn't really matter, we just need a Hannan consistent policy, something with asymptotically zero average regret, and then things are going to work out essentially. So there are lots of Hannan consistent policies. Obviously Hannan was one, and then not long after that, Blackwell's original paper in 1956 gives a way of achieving a kind of regret of square root of n. Also in the adversarial setting, you've got Littlestone and Wormuth's X3 algorithm. Also in the bandit setting, you can do the same. Sorry, the bandit setting is the X3 algorithm. Littlestone Wormuth is called the exponential weighted forecaster. Each of those, so both outside and inside the bandit setting, you can get Hannan consistency. You can also do it in terms of online convex optimization, so you don't need to assume that the scheduling set is some finite discrete set. You can also get Hannan consistency there. And if you've got strict convexity of your objective functions here, you can improve the regret bound to be logarithmic in n. Okay, so essentially any algorithm that you can write that has low regret can be applied to a single server queuing problem that's been considered in both in the paper and subsequent works. And so the kind of conclusion I came out from that was that you don't really need specialized learning algorithms in order to minimize queue size. It's just a matter of taking the algorithm that's there, okay, being a little bit careful in how it's applied in Linley's recursion, and then you're always going to have a good notion of stability from a good learning algorithm, essentially. So that contrasts the other works maybe a little bit, where the conclusion is we need to kind of develop a new algorithm, a special queuing regret algorithm. Okay, whereas here we see that essentially any algorithm will work. Right. So then the next thing I thought about was a little bit about how maybe in a more complicated scheduling setting, maybe the kind of role of learning come in. And so I started thinking a little bit about MaxWeight with respect to things like Hannan consistency and Blackwell approachability. I didn't discuss this too much actually in the paper, it was more just a small remark. But it's the reason, although you can start to incorporate learning ideas into MaxWeight, my feeling from sort of analysing the algorithm and thinking about it one way is that actually it is already a Hannan consistent or Blackwell approach to looking at minimising queue length. Okay, so if we want to look at something like MaxWeight, and just to recall, MaxWeight is a system where you have more than one queue, and then you have servers, but you also have constraints on the servers. So in this instance, if there's a line between two of the servers, then you can't serve them simultaneously. So I can't serve this at the same time as this, but I can serve this at the same time as this. Okay. Right, and what MaxWeight says we should do is always choose the service decision that maximizes the sum of the queue lengths. So if I think of sigma j here being the amount of service I commit to qj, then I multiply that by the queue length and make the service scheduling decision that maximizes the sum of those. Okay. Now, so you can start to think about how maybe regret or learning algorithms apply in the MaxWeight setting, or indeed back pressure, which is a related algorithm. However, if you kind of look at the stability proof for MaxWeight, so it's known that MaxWeight is stable whenever there is a policy that will stabilize the network. So it's got this kind of great robust stability property, being both adaptive and being able to stable for any subcritical arrival rate. However, if you go through the proof of max weight stability, what you do is it's a Lyapunov function argument, and you consider a quadratic Lyapunov function. So you kind of look at the difference in the squares of the sums of the Q lengths, and when you expand it out, okay, what you can end up with is noticing that you end up with a kind of maximization over the set of schedules minimized over the worst case kind of Q lengths. All right, and we know by the minimax theorem that we can always swap the maximum over the schedules and the minimizations over the different Q length distributions that we can have. Okay, and because we can do that switch, swapping these two with each other, then we can essentially end up with a stability criteria that says it's stable no matter what the Q lengths are. There's a schedule that we decide based on that always stabilizes the system. Okay, so essentially because there's this minimax swap over the vectors of Q lengths, you can actually notice that max weight really is just exactly the same as the application of this vector minimax theorem that you see in Blackwell's approachability theorem. Okay, so in some sense, one way of thinking about what max weight is doing is it's essentially applying Blackwell approachability, which we know is equivalent to Hannan consistency. So one interpretation of max weight, why it's got these good robust stability properties, is because it's already doing the Hannan consistency, regret minimization, approachability, Blackwell work for us. Okay, and so I think this is something that's sort of known, at least sort of there are ideas of that type in Neely's work on universal scheduling in 2010, but really kind of goes back to the original paper of Tassius and Ephraimides. Both Tassius and Ephraimides and Blackwell essentially use the same set of ideas for a quadratic Lyapunov function, and the idea that you have to swap the min and the max in a kind of minimax type game theoretic setting. Okay, so if you look at it that way, then really the kind of complex scheduling problem is already kind of within this class of learning algorithms, and that's the reason it's got these kind of nice results associated with it. So that was my reason for not going quite as far down that route in terms of max weight and learning and scheduling. Right, so instead we're going to talk about two different models related to non-stochastic queuing. So here's another example, a bit like max weight, where it's got this nice property that there is a policy that always stabilizes the system below some threshold, and above some threshold there's no policy that can stabilize the system. Okay, so just to kind of give an idea of other models where maybe that kind of same structure that you see in the max weight occurs. So this is a model that was probably quite popular around the time when I wrote the paper, which is called the vacuum cleaner problem. And the idea is that you've got some square, and then over time bits of dust fall down in space. And then you're kind of in control of this black vacuum cleaner over here, and you're allowed to move around at unit speed, hoovering up the bits of dust. Okay? And we're assuming it doesn't take any time to pick up the dust, but there is obviously the time to travel between the different points. Okay? Now, at this time, there was a lot of interest in kind of nearest neighbor kind of models, but in what I wrote about, what I was interested in is like, what is the notion of stability for this problem? Okay? Because what you can find is that actually, for any fixed speed that the points rain down on, you can always stabilize this model. Okay, so there's always a way that although you could have quite a fast speed that points rain down on, they've also then got to be fairly dense in space, and so the vacuum cleaner can always pick them up at unit speed because they're going to be quite close to each other at the points. Okay, so here in this example, it's interesting what is actually what is a reasonable notion of stability. Before, Hannan consistency seemed to be a reasonable, or low regret seemed to be a reasonable notion of stability in a queuing system where you don't have stochastic arrivals. Okay, but what about this system? What's a reasonable notion of stability here? Okay, so what you can prove, and the theorem we proved in the paper is that suppose the arrival rate is sort of t to some power alpha. Okay, so here I'm really assuming that rather than just t being some power of t, it's actually a Lipschitz function. But let's just assume that, it's sort of roughly t to the power of alpha is the arrival rate. Okay, then you can prove that if alpha is less than 2, okay, so the power, so it could be up to anything up to like a quadratic rate, arrival rate over time, then there exists a policy such that the queue length remains of lower order than the arrival rate. So a bit like the notion of stability before. As long as the queue length is small order compared to the arrival rate, then we can say it's stable, but otherwise it's not stable. If it grows, say, linearly or proportional to the arrival rate, then it's not. So particularly you can show that as long as alpha is bigger than 2, okay, so it's not the arrival rate, but the power of the arrival rate is bigger than 2, then for every policy, the queue length is actually proportional to the number of arrivals. So it's a very similar statement to the MaxWeight algorithm, but rather than being a linear property, it's a property in terms of the powers of alpha. Okay, and I'll explain a little bit how the proof works for that. So the idea is to use an old idea of Bartoli and plasma, which is to use a space-filling curve heuristic. Okay, the idea is that for each point that rains down in space, you can essentially give it a decimal expansion. Okay, so here you could think of giving everything in this square a 0, this being 0.1, this being 0.2, this being 0.3. Okay, and then everything in this square is 0.4, starting with 0.4, 0.41, 0.42. Notice it's following essentially the same path. Okay, here. And then everything's 0.5 in here, 0.6. And essentially you can imagine by this argument we've essentially constructed, and then within each of these spares we can construct the same path. Okay, now this path is called a space filling curve. Notice we've essentially come up with a way of essentially writing the two-dimensional square here in terms of a one-dimensional curve. Okay, and one thing you can show about the space filling curve is it's sort of alpha holder continuous, where alpha is equal to a half. Okay, in other words, it's not quite sort of Lipschitz continuous, but sort of Lipschitz continuous like the square root here. Okay, and what you can essentially show is that the kind of half in here is sort of 1 over that half is the thing that gives you your kind of maximum rate of service. Okay, so somehow that's the speed at which your Hoover can move around through this decimal expansion over here. Whereas if we get alpha bigger than 2, then there's nothing we can do. We can always put points sort of in the grid corners, filling up the grid corners, and then filling up the finer grid corners, and keeping on going, and you can never essentially move fast enough because of this bound to cover all of the points in space. Okay, so that's roughly at a high level how the proof works there. It should be remarked also about that time Lendros Tassioulis emailed me to mention that he had a similar kind of idea of adversarial stability in the case alpha equals 1. Okay, so it is possible to prove, there was earlier work indeed, and we referenced that in the paper, covering the kind of adversarial stability in the case alpha equals 1. Okay. Right, so so now that we've covered those two main models, the simple regret queue and also this kind of non-stochastic vacuum cleaner problem, as well as the kind of segue into how MaxWeight relates to Blackwell approachability and Hannan consistency, let's kind of conclude. So in general, sort of after writing the paper, my feeling was that, we didn't really need sort of specialized learning algorithms to apply to queuing systems. It was that you could take an off-the-shelf learning algorithm and then apply it to the queuing system and it should work. We don't need to kind of necessarily invent a new algorithm to get things to work. On the other hand, we do need to understand how the errors propagate through the system in order to get an idea of if it's going to work. Okay, and in the simple regret queue, for example, we found that essentially the rate of convergence of the regret correspond exactly to the rate of convergence in the queuing system, assuming there was a policy that stabilized the system. Okay, so the other thing is that the regret and approachability does have an impact on the stability of the system. So essentially the regret bound that you have associated with the learning algorithm seems to impact on what the stability region is of the system. So that was true for all three of the examples covered so far. The ability of you to learn the rates, either in terms of dominating the arrival rate in max weight, in terms of the extra error bound that you get in the simple regret queue, or the ability of the space filling curve to cover space in time. All of those essentially were the fundamental things that gave the impact on the stability. Okay, and just finally, there's kind of a references here. So yeah, one's the kind of the original paper here, and like I say, had a good chat with Dev Everett about his kind of thoughts on the problem as well, around about the kind of YECT 5. So you know, he had an independent set of ideas on that, and had a lot of interesting ideas in terms of the CMU rule, which were later actually done independently by a separate set of authors. And I should say that, you know, the ideas of kind of non-stochasticity in queuing is not a new idea, and learning queuing is not a new idea necessarily. So although the idea of regret in queuing seems to have come up a lot more, but there are certainly other papers that consider that. So, you know, the kind of literature on, particularly on adversarial queuing, is a kind of common way of thinking about kind of non-stochasticity, and also within the kind of spatial models there's also that kind of aspect as well. And the classical kind of works there are the kind of Bartholdi, Birdwood, Hamilton, Hammersley results. Okay, great. Okay, well, thank you again for having me, and thanks for listening online if you managed to follow this talk. It's a strange one not having an audience in front of you when you're doing your recording, so hopefully there's some chance to interact in person as well.